Okay, calculus, we're going to pick up now the second part of our 3.8 notes. There might be a third, there might not. We'll see how I'm doing on time here by the end of the day. But the second thing we're going to talk about here within 3.8, as I said earlier, is something that almost every other calculus book that I have seen puts in a separate section. But your author decided to include this here, and I'll try to explain why that is. And that is the concept of the derivatives of the inverse trig functions right here. So earlier on in this chapter, I believe in section 3.6, we did the derivatives of all of your trig functions. The derivative of sine of an angle is cosine of the same angle, and so on and so forth. Now we're going to start talking about the 6 inverse trig functions. Before we do that, let me take just a moment, and I just want to make sure that everybody understands what in the world we are talking about with inverse trig. Let me start off with a statement that I'm hoping you guys understand pretty well, guys. The sine of pi over 6, if we're talking radians, is equal to 1/2. That is a true statement. At least I certainly hope it is, or I'll be terribly embarrassed. But I want to make sure that everybody understands here that when you are taking the sine of a number, in this case pi over 6, that number is an angle. And the answer you get when you take the sine of an angle, very simply, is called a ratio. So as I'm thinking you guys know already, pi over 6 is a 30-degree angle on the unit circle right over here. All right, so we've got pi over 6 for the measure of this angle. And there's a couple of different ways you could label the sides within this triangle right here. You could say sine is my opposite leg over my hypotenuse, so my opposite leg is 1 and my hypotenuse is 2. That certainly is one way to do it. The only problem here is this isn't really what we consider to be a unit circle. A unit circle, which really we should be focusing on, has a radius of 1. So in that case, guys, the sine value on a unit circle is simply equal to the y coordinate at this point, so that's a 1/2 right there. And if you remember, this side over here is a √3/2. So that, everybody, pardon me for patronizing you a little bit, that is a quick little explanation of basic trig. My next question then would be, do we understand this concept? What if I were to ask you guys this question? What is the inverse sine, and let me mix things up just a little bit, of √2/2? Now, whether or not you know the answer to that, I'm more interested in, do we understand the question? That's what's important. Now, sine and inverse sine are different things. And the main difference here is that the √2/2 that we're being asked to take the inverse sine of, guys, that's not an angle. That is the ratio. And the answer to an inverse trig problem is the angle that we're working on right here. Okay, so there's a different question here between basic trig over here on the left and inverse trig over here on the right. With basic trig, they give you the ratio, they give you the angle, and you've got to figure out what the numerical ratio of opposite leg to hypotenuse is. But with inverse trig, they give you the inverse sine and they give you the ratio, and you're now trying to come up with what angle on the unit circle has a sine value of √2/2. Now that's a little funny too. There's actually an infinite number of answers to that question, but because of something we talked very briefly about back in chapter 1 called principal inverse sine, there's only one angle in quadrants 1 or 4, everybody, from an angle of -pi/2 at 6 o'clock up to pi/2 at 12 o'clock that has a sine ratio equal to this, √2/2, and the answer to that is pi/4. So I need to make sure everybody understands the difference between inverse sine and regular sine. So with that in mind, that's going to explain some of these answers here in a moment. But for now, let's cut to the chase. Let's go ahead and fill this in. I am going to show you guys in detail where one of these answers comes from. And trust me, after that, you will be so amazed, or you will so not care, that nobody will ask to see the other 5, I promise. But here goes. Guys, the derivative of inverse sine, and let me focus right here, of u. Now that should give you pause for just a moment. We're taking a derivative with respect to x, but I didn't put an x here, I put a u. And so I wanted you guys to recall this little tidbit that we use a lot as a shorthand notation in calculus. U represents a function of x. So even though it looks right over here like x is x and u is u, and it looks like they're two different variables, which doesn't make sense, they're not. U is actually a function of x. It's just going to look different in each individual problem. Okay, so that being said, here's your first big one, guys. The derivative with respect to x of the inverse sine of u being some ratio, is a 1 on top divided by the square root of 1 minus u squared. Ugly. But wait, there's more. Times the derivative of u taken with respect to x. And I'm hoping you guys recognize that that last little tidbit, that last factor there, that's the chain rule, times the derivative of u with respect to x. So what I'm going to say right now, guys, and it really pains me to say this, is that what I'm about to show you next is really not necessary to you guys being able to understand and to do problems like this, but I want to take a moment and explain what's going on here. And this will also explain why this concept of inverse trig derivatives is included here in section 3.8, where we're taking the derivative of inverse functions. So what we're going to say right here, guys, is that an original equation here, y, is equal to the inverse sine, and I'm just going to go with x here, not u, just to make things nice and simple. Okay, so if y is equal to the inverse sine of u, we eventually want to find the derivative of y with respect to x. That's what we're going for. Unfortunately, unless we're using the formula that we're trying to prove, which is circular reasoning and a big mathematical no-no, we don't know right now what the derivative of inverse sine of x is. So what I'm going to do instead is take the sine of the right side and balance that out by taking the sine of the left side of this equation. Well, the sine and the inverse sine cancel, and we've now rewritten this as the sine of y is simply equal to x. And now, what we have, everybody, I'm hoping you recognize now, sine of y equals x is an implicitly defined equation. The equation that we have, the way it's written right now, is not solved for y in terms of x. That's what we had right here, but that was a dead end because we didn't know how to take the derivative of inverse sine of x. So we can write the equation implicitly and now try implicit differentiation. Let's differentiate both sides of this equation with respect to x. Okay, left side. The derivative of sine of any angle is cosine of the same angle multiplied by the derivative of y with respect to x, chain rule, equals the derivative with respect to x of x is just 1. Now our goal here, as always, is to find dy dx. So to get dy dx by itself, we would divide both sides by the cosine of y. That's certainly not wrong, but you guys know that in higher levels of math, it's a little bit silly to write something like 1 over cosine of y. That's the reciprocal of cosine of y, and we have a name for that, ladies and gentlemen. That's called secant of y. So the derivative of y with respect to x is secant of y. Now you will notice that is certainly not what we wrote down right here. So what gives? Well, the important thing is that really, as we're filling in this table, we want all of these derivatives to be written in terms of u, which really means they're going to be written in terms of x. And right now, this derivative that we just found, the derivative of inverse sine of x is secant of y. Well, that derivative is not written in terms of x. It's written in terms of y. So what we want to try to do is to take advantage of the original statement that we were given, y is equal to the inverse sine of x, and see if we can't figure out what that means and if there isn't another way of writing the secant of y. So we go back to the original statement, guys. Y is equal to the inverse sine of x. Now what does that mean? X is the ratio and y is the angle that has a sine equal to x. Actually, that might have been easier to see right here. The sine of y is equal to x. So I'm going to draw myself a first quadrant angle. I don't really know what it is and I don't really care what it is. But in a first quadrant angle, the angle we're taking the sine of, everybody, is y. I'm not going to put a degree sign there because this could be in radians. Y is the angle. And the sine ratio of y, the sine of y, is equal to x. And sine is opposite leg, so that's x, over hypotenuse, which would be 1. So the way I've drawn that figure, that supports this idea right here, that y is equal to the inverse sine of x, or if you wanted to look at it a different way, that the sine of y is equal to x, or x over 1. Now the fun part, everybody. You have a right triangle here in this diagram. The hypotenuse is 1. One of the legs is x. Once you know two sides in a right triangle, you know the third by using the Pythagorean theorem. So I'm going to skip through a lot of work right here, but this other leg right here ends up being the square root of your hypotenuse squared, which is 1, minus the other leg squared, which is x squared. So the square root of 1 minus x squared is the length of this horizontal leg here in this particular triangle. And look at where we are right here, guys. Our derivative is the secant of y. Well, here's your angle y, and the secant, everybody, I guess let's write this here, dy dx is equal to, secant of y is the reciprocal of its cosine. The cosine of y would be adjacent leg over hypotenuse. The secant then is the hypotenuse over the adjacent leg. Hypotenuse is 1 and the adjacent leg is the square root of 1 minus x squared. And that, everybody, is the formula that we were looking for that we just wrote down. I just simplified it with an x rather than with a u right there. All right, so again, to be very clear, none of this is necessary for you guys to know. I just hate treating you like children and spoon-feeding you information at this point and asking you guys just to believe me. All right, so that, everybody, is where this formula here comes from. And as I said, nobody cares where the other ones do, although they all work out in a similar way. And if anybody wants to see them, feel free to make an appointment at office hours. Good news, everybody. The derivative of inverse cosine of u is almost identical to what we just wrote down. It just is the opposite. So this is going to be a negative 1 over the square root of 1 minus a u squared multiplied now by, nope, that's not it, multiplied now by a du dx with the chain rule right there. Okay, we're in good shape. One thing, let me say this real quick, that should worry you guys. What if, like, I don't know, what if u was 3? Don't we have a problem right here? Because that becomes 1 minus 3 squared. That's 1 minus 9, which is negative 8. And the square root of negative 8 is an imaginary number. That would be a problem. But the good news is, everybody, is that if we recall, u is not just a random number, and it's not an angle. U is the ratio. And the question of inverse sine of u is asking you what angle has a sine equal to this u ratio. Well, remember, guys, that the range of the sine function, it can never be bigger than 1, and it can never be less than negative 1. So there's no way that u could ever equal 3. U more likely is going to be something like, well, what could you get for a sine value? Something like 1/2, or root 2 over 2, or 3. Root 3 over 2. And in any one of those cases, 1 minus u squared is going to end up being positive, and therefore you'll end up with a real result here. So I'm sure you were all terribly worried about that. That takes care of that. Shut up, Fontana. Finish it up. All right, the next one is the easiest of the bunch. The derivative with respect to x of inverse tangent of u is simply a 1 over a 1 plus u squared. And again, chain rule, we multiply that by a du dx. No square roots there. You will often see that denominator written backwards as u squared plus 1. I honestly don't remember which way your author wrote it, but who cares? It's the addition property, it's commutative, they both work. Okay, more good news. I'm going to move over to the right now. the derivative with respect to x of inverse cotangent of u is simply going to be the opposite of this one right here. So that's going to be a negative 1 over a 1 plus a u squared multiplied now by a du dx. So that's something, guys. This stuff is not easy, and yes, at some point you are going to have it memorized, but the good news is the inverse cosine derivative is just the opposite of inverse sine. The inverse cotangent derivative is just the opposite of the inverse tangent derivative. And that pattern continues. I'm going to go up the list here. I'm going to go now to the derivative with respect to x of inverse secant of u. This is the most complicated of the bunch, everybody. There's a 1 on top here. There's an absolute value of u, and that now gets multiplied by the square root of u squared minus 1. Whew! That's a lot. Uh-oh, I don't know what I just did, but I think it's bad. All right, that, but we're not done there, times, once again, the derivative of u taken with respect to x. Okay, so that's what's going on right there. And the last one, everybody, the derivative of inverse cosecant is simply the opposite of the inverse secant derivative that we just wrote down. Negative 1 over the absolute value of u times the square root of u squared minus 1 multiplied now by the derivative of u with respect to x. So all right, everybody, those are your 6 inverse trigonometric function derivatives, and we need to have those, well, normally I'd say we need to have those memorized for our next quiz or test. All right, let's see those in action. So that was loads of fun. So was that. Let's start doing some real problems. I think I've got 4 of these examples to do with you guys. Y is equal to the inverse tangent of 5x. All right, this one, everybody, technically is written explicitly. It is solved for y on the left, and the right side is expressed solely in terms of x. So we don't really have to worry about implicit differentiation if we know all 6 of those formulas. So what's happening here, guys, is that this 5x, that's our u value right here, if we were to go back and read it out of the chart. So the derivative of y with respect to x of the inverse tangent of any ratio is 1 over, although honestly, guys, we should probably get in the habit of not putting that 1 there. I'll explain why in a minute. It's 1 over u squared plus 1. Well, u, our angle, is 5x. Squaring that is going to get us a 25x squared and a plus 1 there. So that's 1 over u squared plus 1. But wait, there's more, times the derivative of the ratio. And the derivative of 5x is just 5. There isn't a whole lot to do to be able to simplify this, but maybe now you guys see what I meant here when I said we probably shouldn't have written the 1 right there. The one thing you can do is multiply the 1 times the 5 from the chain rule and make this a 5 over a 25x squared plus 1. And that, everybody, is as good as it's going to get. So there's the derivative of y with respect to x. That's it. Okay? Not saying that was easy, but once you know the formula, it's not really all that bad. Next, let's do an inverse sine derivative right here. Okay, solve for y. So we're taking the derivative of y. Careful here, guys. Our variable is not x. This is the derivative of y with respect to t. Will you lose points if you screw that up on a test and you write dy dx? Probably not, but I'll probably give you the angry face just so you know. All right, the derivative of inverse sine of any ratio is 1 over, although I'm not going to write the 1 there yet, so it's 1 over the square root of 1 minus u squared. And u is that ratio right there. So that's a 1 minus t squared. But wait, there's more. Times the derivative of u taken with respect to x, or in this case, the derivative of u with respect to t. And the derivative of 1 minus t is just going to be a negative 1. So that takes care of the chain rule there as well. Is there anything we can do to clean this up? Yeah. Down in the denominator, I don't know if you guys see it yet, something's going to happen, and it's not much, but it's a little bit. So let's go for it. Negative 1 over, we've got a square root of 1 minus. And now let me do this in parentheses, you guys, because we're subtracting. This binomial, 1 minus t squared, expands into 1. That's going to be a minus 2t and then a plus t squared. Okay, that's what happens when we expand the 1 minus t quantity squared. And now the derivative of y with respect, nope, I did it, is respect to t is equal to a negative 1 on top. And then down on the bottom, it's going to be the square root of, and I think you guys can see it, the negative distributes inside here, and your very first two terms are going to be 1 minus 1. Gone. All right, but the minus negative 2t becomes a plus 2t, and the minus t squared is minus t squared. That's where we're at. The only other thing you could maybe do is factor a t out of those two terms in the denominator, but nothing's going to cancel, nothing's a perfect square, I don't see any point to it, so that's what we've got now, guys, for the derivative of y with respect to t. Next, all right, C, y equals the inverse cosecant of x over 2. All right, let's get rolling here. The derivative of y, we're back to x now. Derivative of y with respect to x equals, and here we go. The derivative of inverse cosecant of any ratio is going to be negative 1 up on the top. Well, I'm going to put the negative there, but I'm going to leave out the 1 for now. You'll see why in a moment. All over, this was the complicated one, guys, we begin with the absolute value of u, your ratio, which is x over 2, multiplied now by the square root of u squared minus 1. Well, again, u was x over 2, so squaring that is going to get us an x squared over 4. That's u squared minus 1. But wait, there's more, times the derivative of u. The derivative of x over 2, some people way overthink this, you guys. Your u is x over 2. You do not need the quotient rule here because one of the two sides of your fraction is a constant. It's much easier just to think of this as a linear function, 1/2 times x, and the derivative of 1/2 x is just 1/2. It's your coefficient. So that 1/2, I'm just going to multiply by the 1 that was up here, or the negative 1, and make that a negative 1/2. Now this has complex fractions all over the place, so I'm nowhere near done, but it's a start. Okay, that's the calculus. From here on out, this is just a messy algebraic simplification problem, so let's talk about what we can maybe do, okay? Okay, couple things to talk about here. I don't like that 1/2 up on the top, but I think I'm going to leave it there for now. Okay, dy dx is equal to, I'm going to leave the negative 1/2 up on top. I'm going to show you guys something right now that I'm not sure if you know or not. The absolute value of x over 2, well, that 2 on the bottom is positive, which means that the absolute value doesn't really have any impact on the x over 2 in there. So I can rewrite this term right here as 1/2 multiplied by the absolute value of x. That's a type of math, everybody, with factoring out of an absolute value that we're probably not entirely familiar with, but hopefully that makes a little bit of sense. The big progress, though, is down here in the denominator, where we've got the square root of x squared over 4 minus 1. We're going to try to combine those two terms into 1. So the common denominator here is 4. So I'm just going to think of the 1 as being rewritten as a 4 over 4, which of course equals 1. And now this becomes the square root of x squared minus 4 all over 4. Now, I don't know if that seems significant to you guys or not, but let me go slow and see if I can show you why that is important. dy dx equals, I still have, actually, now I think you can see one thing we're going to do. There's a factor of 1/2 on the top, a factor of 1/2 on the bottom. They just cancel each other out. Now, the negative didn't go away, so now I do have that negative 1 up on top, but hey, that's some progress. The absolute value of x leads off. And now in the denominator, you've got the square root of a fraction, which can be broken up into the square root of the numerator, x squared minus 4, over the square root of the denominator, which is 4. See, guys, the significance of this is that that denominator down there is a perfect square. So on my next line, I'm stretching this out, dy dx, that square root of 4 on the bottom just becomes a 2. Negative 1 over the square root of x times, you can't do anything with the square root of x minus 4, okay? But the denominator, the square root of 4, just becomes a 2. And the last thing that I see here that I don't like, we have it as a complex fraction. The denominator of the denominator, which is 2, gets moved up into the numerator, everybody. And this now becomes dy dx is equal to, that's now a negative 2 on top, all over the absolute value of x times the square root of x squared minus 4. And I really do not think, you guys, that this is going to work out any better with any more simplification, so I think that's probably a good spot to quit on that problem right there. I don't see anything else to be gained by attempting to go any further. Okay? All right, so that is a pretty tough problem right there for example C, and I've got, let's see, a D, and then we'll see how we're doing on that one. For what's next. All right, let's take a look at D. Last one that I've got for you here. This is a problem that is a good example of something I like to talk about once in a while. When I am making problems, and you guys know I make the problems for your quizzes and your tests, when I am making problems, I sometimes have a dilemma. I can make the problems pretty at the beginning, but then they very often end up ugly at the end. I would say that this is a good example. This wasn't that bad of a problem to start with, but it got ugly by the end of it. Or sometimes I can flip that around. Sometimes I can make a problem really, really ugly at the beginning in hopes that it works out pretty nicely at the end. This is an example of what we're talking about here. So, what's going on here, guys? The ratio that we're taking the inverse cosine of is a square root. That's a little weird. I'm going to write that off to the side. U is the square root of 1 minus a 16x squared. Just keep that in mind. We are now taking the derivative of y with respect to x. And dy dx of an inverse cosine function is going to begin with a negative 1, and I know I've been saying not to write it, but I'm going to do it here. A negative 1 all over, oh boy now, the square root of 1 minus u squared. 1 minus u squared. Well, let me go back up here in red. If u is the square root of 1 minus 16x squared, then u squared comes from squaring that right side. It cancels out the square root, and u squared is 1 minus 16x squared. So that's what's going to go here. 1 minus a 16x squared takes the place of the u squared. So where are we? The derivative of inverse cosine of a ratio is negative 1 over the square root of 1 minus u squared, but wait, there's more, times the derivative of u taken with respect to x. Oh boy. So if I need to take the derivative of that u, it's probably a good idea to think about u as a 1 minus 16x squared, and instead of with a square root, let's write it as a 1/2. So the derivative of that, everybody, oh boy, is going to be, I better write this down right here. The derivative of u with respect to x is going to be a 1/2 times a 1 minus 16x squared, drop the power by 1, that's a negative 1/2, times the derivative within. And the derivative of 1 minus 16x squared is going to be a minus 32x. Oh, goodness. All right, so the derivative of u with respect to x could clean up just a little bit here, guys. The 1/2 and the negative 32, that makes a negative 16. The x tags along, and then the negative 1/2 power gives me a square root of 1 minus 16x squared down on the bottom. Ugh, I don't think it's going to get any cleaner than that. So that, everybody in green, is my du dx. I need to multiply this by a negative 16x over the square root of 1 minus 16x squared. Oh, and I apologize, guys. I didn't do a great job of keeping all this stuff separated here, but that's where we are right now. All right, all right. So that's where things stand. I certainly hope this can be simplified because it's pretty ugly the way it is right now. dy dx is equal to, and let's see what we've got. Numerator times numerator, -1 times -16x. Hey, at least it turned positive. That's 16x. Down in the denominator, let's look at what's going on right here, you guys. 1 minus the quantity 1 minus 16x squared. That's a 1 minus 1, gone, and the opposite of -16x squared is 16x squared. All of that is my radicand, so there's a square root here of 16x squared. That wasn't terrible. And then I still have the second denominator, the square root of 1 minus 16x squared, and I don't know if I can do anything with that. But we are making progress, and I think you guys saw it. In the first radical in the denominator, our radicand ended up being a perfect square. So dy dx is going to equal a 16x on top, and down on the bottom, the square root of 16x squared is just a 4x. That gets multiplied by a 1 minus a 16x squared, and now I hope you guys see it, the 16x and the 4x can be simplified here. dy dx is simply going to equal a 4 over the square root of 1 minus a 16x squared. That is not what you'd call a super pretty answer, you guys, but it's a lot better than it was earlier. I don't think there's anything else we can do to simplify that any further, so I'm pretty confident in saying that that, as it is, everybody, is going to be the final answer to this problem right over here. So certainly not easy, but hopefully that makes a little bit of sense. You guys are going to struggle with these problems. You know why? Because they're difficult. But you need to work through them, check your answers, ask some questions if there are things on there that you don't understand, but try to keep everything in mind in terms of the formulas that we've been discussing and remembering the omnipresent chain rule, which never goes away, everybody. Okay, I'm going to end this video right there. This would be a great time for you guys to go work on the homework that dealt with just the derivatives of the inverse trigonometric functions, and then when we come back, we'll finish off the last one concept here in section 3.8. Good luck, guys.